at Stockholm University, and I think many of you already know her, so I will not give a long introduction, except saying that her group works with everything from lab measurements to global modeling of aerosols, clouds, and climate. And Ulrika is here today and tomorrow, and there's some time still tomorrow to talk to her if you have time and want to get some feedback on your work or something, so she's here. So today we will hear about if climate change should be tackled with climate invention, and I guess this is a super relevant topic at the moment. So please, Ulrika.
Yeah, I'm not sure. I'm not on, or am I? I am, because I was going to do it the other way around.
It's being recorded because we have some people that...
Yeah, perfect. But are you still hearing me? Are you sure? Okay, good. Okay, so yes. When Annika asked me for what I wanted to talk about, I thought I do it simple, because there was a... Hi, Ilona. We had a summer school on climate engineering or climate invention, or however it's called, in Switzerland not long ago, and so yes, and I was actually surprised that nowadays there's whole summer schools devoted to this topic. So it is of course an obvious question, and the question is where does tackling or perturbing the system starts with? Is like, should we do it at all? Is it okay if it's done just as a byproduct for, I don't know, reducing hail damage? Or if you don't like the clouds, should you do something about them? Or should you actually do it on the long run? Well, so Annika was asking me what this figure is, because this is one of the examples where you actually do see that this is not natural. I mean, it's a natural process if you have super cool cloud droplets here, and for whatever reason you form some ice crystals, that the ice crystals will grow at the expense of the cloud droplets. That is a natural process. But a hole in the sky is normally nothing that you see just by chance. And so this here is just a byproduct of aviation, and time to time when you have a starting airplane and you have, after the engines, what? Yeah. You can see that, you can actually get in the turbulent wakes afterwards, you can find that you have expansions and cooling of up to 20 degrees. So you get 20-degree colder temperatures, and if that's sufficient for ice crystals to form and grow, then you will convert at least this part of a bit from a supercooled altocumulus cloud, in that case, into some ice that falls, because thermodynamically it's not stable to have water and ice. So yeah, but this is a very small scale, and you wouldn't even think of calling that climate invention. It's not even weather modification. It's just a byproduct of that you see visually, that we are actually sometimes changing clouds already now. Okay, why is this discussion about climate intervention? Where is it coming from? It comes from that for the longest time, I mean, since the first IPCC reports, it was always said, well, it's getting warmer. Depending on how much we do, we will have temperatures 4 degrees more than today, or maybe just 1 or 2. But you all know that there was the Paris Agreement in 2015, which said we should hold the increase in the global average temperature to well below 2 degrees above pre-industrial, and probably even 1.5, and at the moment we are at 1, or if you looked at the last 5 years, it's 1.1 already, so we are really close to be there. So yeah, if you look where we are at the moment, 2017, with the human-induced warming, and if you see that there's 1.5, this is going to be reached in 20 times, so especially the younger ones from you will definitely experience something like this, or more likely somewhere up there, if nothing is done. Does it matter? Well, it depends on which indicator you are looking at. there was this special IPCC report on the 1.5 degree temperature target. And it looked like what's shown here is the surface temperature increase. This is where we currently are. So this is the average temperatures 2006 to 2015. And then what's shown here in color is the level of additional impact or risk due to climate change. So which regions or which ecosystems will be affected quickest? It's clearly here the warm water corals that may be far away from Sweden, but here the Arctic region, which is much closer to you. And what Caroline just told me from last year's cruise, that the ice has already changed a lot, right? You found already very different climate, much thinner and smaller ice, pack ice there, so things are changing. And so yes, it does matter if you reach 1.5 or if you reach 2. But for the time being, we are not at all on any mitigation pathway. So a low emission scenario starting like this, there's nowhere near to be seen. We still have the normal rising emissions. So what this means, if at one point in time it's really decided that we should do something about global warming, we won't be able to limit the warming below 2 degrees. So there will be some temperature overshoot. And yeah, it's also seen here in terms of the CO2 input. This is results from Simone Tilms, just to show that. And at one point in time, in order to stabilize climate, you have to come to negative emissions. So you have to withdraw more CO2 from the atmosphere than is going to be put in. And the discussion or the topic of what I'll be spending time on today is to think about, if you don't want this overshoot, is there anything that can be done? Is there any short-term solution out there, any short-term measure, or maybe medium, it depends how long you call that. But is there a role for changing anything else in the climate system in order to avoid this? And the example that she has put in here is, we know we have volcanic eruptions. We know that after volcanic eruption it gets colder. That would be the example if you just inject amounts of sulfur in the stratosphere and have a cooling, and do that as long as needed before we have efficient emission reduction and CO2 drawdown from the atmosphere. That would be the idea or the setup. So yes, so the idea of climate invention would be to reduce the worst impacts of climate change and avoid tipping points. And in this example, then her simulation, it's 160 years of 8 teragram sulfur per year. I'll put that a little bit more into context later on. So what options are there? Actually, IPCC already, the last time around in 2013, discussed a lot of them. And normally it's divided into those where you remove carbon dioxide from the atmosphere, and you do that either because you fertilize the ocean, or you have artificial trees in the atmosphere where the CO2 is being captured, or you reforest or afforest, enhance weathering. There's different possibilities, but I'm not going to talk about them. I'll rather talk about this second group here. That's called, in the IPCC it was still called solar radiation management, and there's a few things that are more, those things are related to aerosols and clouds normally. So here you try to reflect more shortwave radiation, or have permanent, permanent volcanoes, or mirrors in space, or brighter surfaces. Pretty much that's the range there. Oh, sorry, that was too quick. Here we go. Is that right? Yes. So, if you look at this, how would you go about it? If you look at the energy budget, what you see here, you have, of the 340 watts per meter square that enter the atmosphere, Earth atmosphere system, you reflect 76 by clouds, aerosols and gases. And clouds are by far the biggest contributor. They reflect approximately 47 watts per meter square. So half of all the shortwave radiation that gets reflected. So if you think of that CO2 doubling as approximately 4 degrees, if you change these clouds by roughly 10%, you could offset CO2 doubling. So 10% more thick, low-level clouds is what would do the trick. And it's pretty much, it's the low-level clouds that are thick enough that reflect the shortwave radiation best. The cirrus clouds here, they are more or less semi-transparent to sunlight, so you would have to increase them way more to get a similar change in reflectivity. But most important, the cirrus clouds are shown here because they are so cold, and so if they absorb terrestrial radiation from the Earth, they emit it at very, very cold temperatures, much colder as if you had radiation from the atmosphere being emitted to space. So they effectively act as greenhouse gases, similar to greenhouse gases. Their effect in the long wave with keeping back radiation in the Earth's atmosphere system is larger than how much radiation they reflect. So the way you would think of changing them is to reduce them. Getting rid of cirrus clouds would do the trick as well. So either more low-level clouds or less cirrus clouds. Both of those would help. If I say that in Zurich, then I would show you this example for the low-level clouds, because everybody in Zurich and Switzerland knows about that very often in winter we are already under a persistent stratostack, and that's not nice. And the prospect of increasing that even more is not tempting, but you have nice sun, so maybe for you it doesn't matter if there's a few more low-level clouds. Huh? In November.
In November.
There's almost no sunlight.
Yeah, see? Yes, exactly. We just steal you the nice summer. So here's the example of a volcano. But here you see the problem with cirrus clouds is, I mean, this is just a picture of contrails. And for the time being, we don't even know how to avoid contrails. So getting rid of all the cirrus clouds would mean that you are also able as a starting point, to reduce all the contrails, and then you reduce even more of the natural clouds with that. So for the time being, we're doing the opposite. With the producing contrails, it goes in a little bit of increasing the warming that we have. Okay, before I go into the details, there has been changes in terminology, and such that it's not called geoengineering anymore, because geoengineering sounds like activities beyond climate, so that you really do geological engineering and hammer or I don't know what. And it's also not called climate engineering, because that means that we actually know what we are doing. Exactly. And it really implies a later level of precision and control than would be possible. So that's why it's nowadays called climate intervention, because that also sounds like as if it is an action intended to improve the situation. So it also sounds positive. If it is, we can discuss. And the other thing is that solar radiation management is also too narrow, because I just told you for the cirrus clouds that you try to or would need to remove, their main effect is in the terrestrial radiation, so thermal wouldn't be right. Yes. Yes, and albedo modification you could also say, because then really this describes the subset of the radiation management techniques where you really try to increase reflectivity. Okay, so starting with stratospheric aerosol injections. That is the thing that has been received the most attention, for one, because it was the former, for one reason I think, it was the former Nobel laureate Paul Crutzen, Nobel laureate Paul Crutzen, who put up the idea approximately 10 years or a little bit more ago. And he was just looking at the atmosphere, and correctly so, and realizing, well, I mean, we have volcanic eruptions. We know that after a volcanic eruption where a volcano reaches the stratosphere, you have oxidation of sulfur dioxide to sulfuric acid, and those sulfuric acid aerosols reflect sunlight. We have seen it after the Mount Pinatubo, and that's the next example here. If you look, the last large eruption that we had here in 91, Mount Pinatubo, you see that this is like the blue, red, and green curves are observations. So you see that there is a drop in global mean temperature of approximately 0.3 degrees. And the models, actually everything in orange is models, so they also capture this decrease. The other thing that you pick up here is that after a while, you are back to where you were without the volcano. So you would have to have a volcano that is there, for one, permanently and increasing in strength, because as long as the current level of warming is increasing, you would need an increasingly larger amount of sulfur into the stratosphere to keep temperatures constant. But if it works, I mean, this example shows you this is probably as close to a natural analogon that we have. And it was discussed in the 2013 IPCC report, because there have been, it's a model intercomparison study where the models were tasked to change, in this case, the solar constant, to reduce the solar constant more and more and more to keep the temperature constant. So that would be like mirrors in space that you have increasingly more. And yes, in a model world it works, so you can do that for 50 years maybe. And if that at one point, whoever decides to put it up decides this is not a good idea any longer, and we haven't done anything to reduce greenhouse gases, so this gray here is a 1% CO2 increase per year, then you see that very quickly, roughly within a decade, you are back to temperatures that you had without any intervention. And if already now there is the concern that some ecosystems cannot cope with the level of climate change, of warming, the current level that we have, this is much, much faster. So that's also one of the problems, is what's called the termination shock. What happens if at this point you decide it's not good anymore? The other aspect is, if you look at the change in precipitation, you'll see that if you hold temperature constant, you cannot hold precipitation constant at the same time. That doesn't work. And that doesn't work because if you look again at the global energy budget, and now we look at something different, we look of that about half of the incoming solar radiation is absorbed at the Earth's surface. And because the Earth is so inefficient in radiating away all the heat, we have latent heat, we have evaporation. And so half of whatever is absorbed at the Earth's surface is evaporation from the ocean or other moist surfaces, and yes, put back into the atmosphere by condensation. What it means is, if you reduce the solar radiation input into the system, you reduce evaporation. And then, in the global annual mean, evaporation equals precipitation. So by reducing evaporation, we reduce precipitation. Now you can turn this around and say, well, at the moment with anthropogenic climate change, precipitation is anyhow increasing. So maybe if we find a level that we have a little bit of temperature increase and more or less constant precip, maybe that would be also an option. But at least that is something to be aware of. And of course, regionally it won't be the same everywhere. Okay. Remaining with stratospheric aerosol injection, the question is then also, where would it be best to emit? And then what you want, if you do that, you would want to emit it somewhere here in the stratosphere, in the tropical stratosphere, because then at least the particles are part of the Brewer-Dobson circulation, and can be taken all the way up and would have the longest lifetime. Whereas if you have any ejections in mid or high latitude, then the particles very quickly would come down. That's also why the Mount Pinatubo was so good in really reducing temperature, because you had an ejection somewhere in the tropics. And there has been, there's zillions of studies. This is just one example of a study where they looked at the effect of the different where to eject aerosols if you wanted to, and whether to do it in terms of SO2 or to do it already as sulfuric acid particles. And what's highlighted here in green is the range where the particles interact most efficiently with the radiation. So if you have, the more particles you have in this size range, the more radiation you reflect back. And what you can take away from here, insulated different scenarios, and you see by eye that you have the biggest impact if you are able to inject sulfuric acid particles of 50 nanometers or 150 nanometers, sorry, and you do that in the tropics. And the reason why SO2 particles start to, they first need to nucleate and form sulfuric acid droplets, but once you have already a large number of pre-existing particles around, the condensation goes more onto pre-existing particles than forming their own particles. So if you want to do something, the most efficient way would be monodisperse sulfuric acid particles. If you're not worried about acid rain. That would be the next question then. But would be really bad in destroying ozone, and I think those are also toxic as far as I know. So there's some other side effects that you probably don't want.
Diamonds looks interesting.
Yeah, diamond may be just a little too expensive, but other than that, they for sure have no acid rain, but they also get a little bit not ozone neutral. Okay, so here's a summary. So it's really a lot. Like once you dig into it, there's a lot that has been written of all the geoclimate engineering, and especially with those. So here, this is Mark Lawrence. He put something. There's a publication in Nature Communication from last year, and he pretty said yes, the aluminum and titan, they are toxic, so you don't really want that. Sulfuric acid, of course, is acidic. Yeah. And some side effects that you have, there's changes in photosynthesis maybe, so that would have then impact of the whole biosphere, also on solar radiation using photovoltaic and all that. So maybe not thought out.
I have a
Yeah, sure, go ahead.
potentially naive question. So, but why is it really difficult to neutralize sulfuric acid instead of producing sulfuric acid particles to neutralize it with something?
I'm not sure why ammonium sulfate isn't
exactly.
discussed. I'm not sure, because you
Is
could.
it so difficult to manage with ammonia?
I don't know. I mean, you could.
Deposited, you would still have it dissolved, and then you still would make it. It would still be like acid rain, right?
I guess so. If the ammonium goes somewhere else.
I think that's
I
how
mean-
it goes. We have ammonium sulfate in acid rain, and that makes acidification and
Yeah.
What? Frida said that.
But what happens? But
eutrophication. So you
But-
get both. You get
right.
downsides.
Yeah, that's right. Yeah,
so it
that's
doesn't
right.
neutralize. I think.
That's
Mm.
right.
Yes.
So.
Good idea, though.
I think it's also that I guess that the amount of bases, the bases are more difficult to kind of control.
Maybe.
Yeah.
maybe.
Yeah. I mean, it would also. I don't know. I mean, at least I could imagine sulfuric acid is easier to handle, because this is basically always liquid, and you don't have to worry about which phase it is in, and you can disperse it more readily. And I mean, maybe it's easier to have it monodispersed, dispersed. I don't know.
Yeah, and then there's the issue with the solubility, because it's of course also the bases have different solubility.
Okay. So then the question is there like this study that I just showed you got an effect of approximately 1 or 2 watts. Here's a study by Ulrike Niemeyer and Claudia Timrek a few years ago. They looked at how much stratospheric aerosol injections, like if they inject more and more and more, what is the cooling? And this, or the forcing, and this scenario in a way would be rather optimistic, because indicated here is the 8.5 watts per meter square that you have in the RCP 8.5 scenario. So that would say if you just inject 100 and something teragram sulfur per year, which is 2/3 of what we currently have, then you can actually negate all the warming to 2100 even in a business as usual scenario. But also here's a but. And that is a newer study by Kleinschmidt et al. Last year. They went to 50 teragram sulfur, and for them it already turned around. And the most they got out is at most 2 watts per meter square. And maybe actually less if you have larger amounts, because the more you inject, the likelihood for the particles to coagulate and become larger and sediment increases. I mean, this is also in their model, they also find that, and that's why you have this E-folding decay. Because it's clearly so the more is in there, the larger is the coagulation. And they had a feedback also that the circulation, the width of the Brewer-Dobson circulation, something like that changed, and the particles were narrower together, which again increased the coagulation likelihood. So it doesn't seem to be solving it all, is the clear take-home message here. Okay, Alan Robock, so this is already 10 years ago, he published a paper on the benefits and risk of stratospheric climate invention. And so, I mean, it's clear why people think about it, because you want to cool, you don't want the sea level rise, maybe increase plant productivity because they do like diffuse light, and in that case you would also reduce this, increase the terrestrial CO2 sink. So this could be all good. But for 6 benefits, there's 17 risks already put out a decade ago. Starting with like droughts in Africa and Asia. Of course, you're not curing the problem. You have increased ocean acidification from increasing CO2 emissions. The ozone we discussed. No more blue skies. I may have a picture of this. Here's one. Somebody tried to mimic that, how this would be the new skies, and that's what you still have here. Yeah, less solar power, environmental impact of implementation, rapid warming is stopped. I also showed you this. Human error, it could go wrong always. Conflicts, yes, you could think of conflicts, because there's still some countries or region who think that they benefit from climate change and more warming, so they may not be agreeing on doing something like that. Yeah, moral hazard. If we did something like that, would we still have any incentive for mitigation? If we had one today, I guess it is. And then the next question, do we have the right to do so? And who is doing that? So there's lots of questions, and it can be a lengthy discussion.
What about the cost?
Yes, he actually, in the same paper, he also estimated different costs. And it depends on whom you talk to. I mean, the easiest is you compare it to a military budget of a given country, and then it's negligible costs. Okay.
Last question.
Yeah, sure.
But so, if also considering the water cycle changes that increase greenhouse gases, the first one could also be framed as less flood.
Yes, exactly. Exactly, and that's actually true. Some aspects of climate engineering in that sense would be good, because you're also reducing the peak temperatures, and you would be reducing extremes. There have been studies on that. So yes, that aspect could go over. And also, I'm not sure, I also thought that for solar power, diffuse radiation isn't the worst, so maybe this could also go over. So maybe there is some more benefits on the benefit side. Okay, so the second would be increasing albedo. And here we have also an analogon, but not a natural analogon, but an anthropogenic pollution analogon. Because from every ship, most of the ships out there at the ocean are still emitting more or less the dirtiest, or use the dirtiest fuels, and they have lots of particle emissions, and so you change clouds. And sometimes you see that, you see it visually here, you see some of the bright stripes behind ships. And my prime example for that is like this. It doesn't work all the time as beautiful as this, but there's a prime example from flights were done around 20 years ago, where you look at the aerosol concentration, and the aerosol concentration within the track is increased tenfold, giving you a threefold increase in cloud droplets, a decrease in cloud droplet radius, and then this increase in albedo that we saw. So that has been then also thought that would be a way to do that. So the question is, where would you want to do that? And in principle, you would want to target here the areas where you have marine stratocumulus, because those are the areas actually where the net effect of clouds in the present day, the cooling is largest. And it is largest because you have a bright cloud over a dark ocean surface. So that's already, though, without any anthropogenic perturbation. In addition, you very often have rather clean air masses making up those clouds naturally. And if that is the case, if you have like in the case where you have a background cloud that's rather clean, and you add something, be it anthropogenic emissions or whatever climate invention particles, you get a huge increase, potentially a large increase in cloud albedo. Whereas if you were to target like polluted clouds over the continents, the same aerosol input wouldn't give you anywhere because you're already saturated. So those would be the areas that would be beneficial to target. But also their potential is not as large. Here's another intercomparison study of a few climate models that looked at the temperature change with and without marine cloud brightening. And what you see there's a huge variation about its effectiveness. This is like 50 years of trying to do that and then stopping. And I mean, the models where you don't see an effect, there's also not much of a termination effect. And those where you see maybe something, there's a bigger termination effect. And the average cooling that you would get is around 1 degree. Here is a comparison. If you take also land surface into account, this is the warming, one example of a warming that you would get by 2 times CO2, so on average 4 degrees. And in this paper, they compared sunshade, so that would be some mirrors in space, and that's by far the way it's set up, the most efficient method, 3.5 out of 4 degrees. And then they tried other things like painting all the roofs white and or using reflective material. So urban and high means that is like in their most realistic scenario what you could achieve, which gives you like a 0.5 degree cooling. For crops, they are trying to plant crops that have a higher reflectivity than those that are dark, no matter if you like them or not. And the other is that you put reflective material in deserts, and that has the largest of the things that they tested, has the largest potential, because I mean, for one, you have the largest areas, and especially the Sahara is in an area where you have lots of sunlight. Yeah. Okay. If one were to do also a pro and con of those, then the potential in cities is low. Ocean, desert is a little better. But all of them require to keep the surfaces clean. I know you know from experience, if you have something that's white, how easy that gets dark. Yes, that would be the end. And then the costs, and because of that, the costs that are associated with them are expensive, because you really have to keep your surfaces clean. What also was found, and this is what you were asking before about, like rain, it can go both ways. So if you do have brighter deserts, that was found to be beneficial, because if you have already now too much monsoon flooding, you would reduce that. And the opposite was found if you make marine clouds brighter. So yes, the hydrological cycle is affected here as well. Okay, and now I have to come to my toy topic, cirrus seeding, because that's actually something where we have been doing some studies. And we started off by looking at the cirrus clouds and asking the question, what would be the maximum potential that we have if we were to get rid of them? So on average, cirrus clouds warm or have a positive radiative effect of 5 watts per meter square. So you see it here. So in principle, if you got rid of all of them, perfect. You have negated a doubling of CO2. You could also do it, if you look here at the breakdown, the long wave effect dominates with 8 watts per meter square, the short wave 3.5. So if you target, for instance, the Arctic at night, in winter, if you were to get rid of them, you would only have a long wave effect, and that would be, yeah, more efficient, because here in the tropics you often have a cancellation between short wave and long wave. How would it work? And that's really science fiction, if you ask me. This assumes that you have an unperturbed cirrus cloud, and an unperturbed cirrus cloud is supposed to be formed by homogeneous freezing of sulfuric acid, and you have many small ice crystals, and then you do get some reflection of shortwave, but more importantly, what the natural cirrus cloud would do, it would absorb quite a lot of the long wave radiation and emit a bit. And now the trick would be to find the right ice nucleating particle, like mineral dust for instance, and to inject it just before a cirrus cloud would form homogeneously. And so that you form it on few large ice crystals. And if you have fewer larger ice crystals, they would do many things. For one, they would reflect less shortwave, but the shortwave is the minor part. But because their optical depth would be less, there is more long wave radiation going to space from the warmer levels below. So you actually have increased emission, long wave emission to space. And plus, these larger ice crystal sediment, they have a shorter lifetime, and you also take some of the water vapor in the upper troposphere with you. So that's all good, if you manage to seed them at the right time. And so the next question is, if you do that seriously, is how often do we actually find cirrus clouds that are formed by homogeneous nucleation of sulfuric acid? In our model, if you look at the areas where we have the highest ice crystal number concentration, which is indicative of this homogeneous nucleation, you see it's pretty much where you have orography. So I'm not sure how easy it is to fly there, for one, or to perturb it, and for two, the areas are rather limited. And here is the observations of ice crystal number concentrations, and they pretty much match what we have in the model, that it's true. High ice crystal number concentrations are where you have orography, but anything else in the globe shouldn't be too much affected. Okay, wait a second, I'm going here so that there's time for question. How efficient is zero seeding? It all started because Trude Storolfmo published a paper in 2014 where she showed here, depending on how many ice nucleating particles you inject, you can find some negative forcing. And she found a forcing of approximately -8 watts per meter square for approximately 20 ice nucleating particles. And what happens from here, if you inject more, is the same what you saw with the ship tracks. That's what's then called overseeding. You inject just so many more ice nucleating particles that the cloud becomes thicker again. And then you have like, that definitely is the wrong way around. Okay, so that was the starting point also for us to look into that. And there appeared 2 studies at a similar time. I found this. Joyce Penner and us, we said, well, sorry Trude, we can't do something that's nearly as negative as what you have here. We find that you go into overseeding or creating more cloud right away. And for us in the model, basically what happens is that we know that from out there are ice supersaturated regions. And if you put ice nucleating particles in, then you just form cirrus clouds where there weren't any before. So you create more. That's why I started out saying if we knew how to get rid of contrails, that would be the first bit. I mean, Blasch then, who worked on that, was very like desperate to see what could we do, how could we tweak the model that we find something. And I think he came up with it was something like, I think if you put in 10 micrometer large particles, like more or less stones up there, then it works. Then also in our model, you get some cooling, but it's then huge amounts that you really would need to put in. But anything that's more realistic in terms of size, no chance. Okay. And here's just a last view of how different our model reacts to the CAM model, which is in a 1.5 times CO2 climate with like our scenario where we achieve the maximum cooling, and that's like 0.5 degree cooling. And here you see Trude's simulations with the CAM model would negate the whole warming from 1.5 times CO2 and actually turn it into the cooling. So there's lots of uncertainty in terms of modeling as to what you think, if there is an effect, and if so, how large it is. Okay. So, where are we at this point? Well, people have tried to look at the different methods that are out there and compare them in terms of how effective they are and also how much it will cost. And so an affordability of 5 to 6 means it's cheap, and down here it's expensive. So easily said, this is a geoengineering or climate invention method that you didn't want, and this would be one that would be good. And of the 3 that I've been showing you, stratospheric aerosols, cirrus, and marine clouds, the stratospheric aerosols is maybe the best. But you can color code it also and add an aspect of safety, which means side effects. And the side effects that we have discussed here with ozone and maybe precipitation and all the other things then tell you, maybe it is effective and also not that expensive, but it comes at a cost of the side effects. And so what you really would want is like the perfect method being also green. So that's not there.
They don't have a feasibility color coding.
No, it comes. There's different versions of it. But my version, I just add in all the other methods that are out there, including carbon dioxide removal. And you see there is nothing close to this bit. I show you something with feasibility, actually. No timeliness. Timeliness is here something else that's sometimes in there. Because what's also disturbing about all of this research, in an overview paper from Oschlies and Klepper, they evaluated the Royal Society report, which was the first to put this comparison up, and re-evaluated that 7 years later. And what you see, what this re-elevation or what all the research in the time has brought you is a decrease in effectiveness and, in this way, in an increase in costs. So there's no cheap solution without side effects. Okay, so with that I stop. So after having said all that, there's no way, instead of reducing CO2 emissions, if you ask me. Because we have, climate invention are not curing the problem. You have this increase in ocean acidification for sure. And all of the methods that have been studied so far can only compensate part of the warming. And they seem to be dominated by negative consequences. So yes, I can only repeat point one. There is nothing apart from reducing greenhouse gas emissions. Okay, with that I thank you for your attention.
Thank you very much for this comprehensive review. It's good to see. So, do we have questions or comments or thoughts? Yeah.
Okay. You just talked about stratospheric particles within the aerosols. Have you also thought about if you put them even higher, for example, into the mesosphere?
I'm personally not, but of course they would have a yet much larger lifetime. The question is, with the costs of getting them up there, how much more expensive they would be. I thought you were going to ask why not troposphere, and I was going to say, well, that's what anthropogenic pollution has done all along, and that's actually why we haven't seen the large amount of warming that we have. But no, I haven't been thinking about the mesosphere. It would for sure be more effective because you had the particles staying around for longer.
And the ozone problem would be there.
Yes, yes. Yes, it's just the question, how do you get them there? But
Yeah.
So how about is there any study like doing several climate intervention methods together so that you reach a optimal point?
yes.
Yeah.
Yes, yeah, good question. I glossed over that. There has been actually several. This is one example. That's an example from Cao et al. And they call it cocktail engineering, exactly what you are saying. And it has been done with different methods like stratospheric aerosol and marine cloud brightening. And here's an example that combines stratospheric aerosol injection with different amounts. So this here is like 44 teragram. And then they also try to look at so here the change in precip and the change in global mean temperature. And you see from stratospheric, so for what I showed you before, so whatever you put in, you have this here. If you go the temperature to 0, precipitation is decreasing. And then they said, well, we combine it now with cirrus cloud thinning. This is what the CCT stands for. And the cirrus cloud thinning, because it mainly affects the long wave radiation, doesn't have such a large impact on the hydrological cycle. And they mimicked cirrus cloud thinning by increasing the fall velocity of the ice crystals. This is why it's 2 times so. And so if you just had cirrus cloud thinning, you wouldn't be, you pretty much have only very, very small decrease in precipitation as compared to where we are as the starting point. But you have this, decrease in temperature. And if you combined it smartly, and I think this is their blue scenario, you could land at a point where you have 0 precipitation change and 0 temperature change.
How would it change regionally then?
I'm not sure.
Changes compensating each other.
I'm not sure if I've seen that. I've only seen that they try to do this only for land, to say it's most important to conserve land precipitation. And then you come up with a different mix of how you would need to combine stratospheric aerosol injection and cirrus cloud thinning. But I'm not sure if in their paper I don't know if they have regionally looked at how this looks like. I would have to go back. It's a good question. Frida?
Do you have any thoughts on feasibility of these methods as compared to CO2 reduction methods? Because I mean, that in a sense is going to be necessary anyway, right? You had the scenarios where you reject aerosols for 200 years, and then we can get back on the 1.5 track. But 1.5 track really assumes a lot of CO2 reduction. So, do you think those are they more feasible?
Well, that was an interesting discussion at the summer school that I attended, because most of the summer school was exactly on this carbon dioxide removal. And they actually, it's very, I mean, the direct air capture, that is a method where you would say if you just put like artificial trees, looks like filters, and you just let the CO2 go through, that at least is not competing with the agricultural area, but it demands a lot of energy. So this is problematic here. Afforestation or reforestation is good because it's a natural process. Just the question is, for it to be effective, do we have enough area? And don't we need some of that for food production? The same actually is with the bioenergy, with carbon capture and storage. The same problem is the land demand. The land demand is the problem for both of those. With the ocean fertilization, so this is here you do put calcium carbonate. Ocean fertilization, like putting iron in there, because there are areas in the ocean that are limited, they have an iron deficiency, similar to as human can, so it helps if you give them iron. And it was actually shown that yes, afterwards you see a bloom in the phytoplankton, so this method seems to work initially. But phytoplankton doesn't mean that the CO2 really comes from the surface water, is drawn down all the way to the deep ocean. And so far that hasn't been shown, that if you really are able to fix more CO2 in the surface ocean, that you really get an increased drawdown, because after this phytoplankton bloom you get just a different species of zooplankton, and yeah, as long as they don't sediment, it didn't seem to help. And then what is left is this accelerated weathering, which is like, there was a German climate engineering program. They made a good movie about these CO2 methods. And the cartoon they used for this to show that this works is like taking a Matterhorn each year or something like that and scrap it to put it into the ocean. Some people think that this may be the best, because that's actually a natural process that happens on very, very long time scales. But yes, I'm not sure. Or what, there is this so-called blue carbon that was also discussed, that I think in the mangroves or the coastal areas, there you can bind a lot of carbon, but it's just that you have very limited spaces where you have coasts. So this is also not a huge potential. So the answer is no, there's also not the solution out there.
Some people also, so you only talked about putting reflectors over deserts, but what about over oceans? Because that has also been suggested, but you never...
Yes, that has been suggested. I've seen that for a study looking at this for the Arctic, just to ensure that you keep some Arctic sea ice or so.
But also over tropical oceans too.
Yeah. The side effect that I've seen with this Arctic ocean reflection was that you had an impact on the thermohaline circulation, and that led to some subsurface warming, which was also not wanted, of course. So also no, as far as I can tell.
think we will thank Ulrika, and if anybody wants to talk to her tomorrow, just let me or Ulrika know, and yeah, you're welcome.